Hello everyone, welcome to my channel Reshma Physics. Now in today's video, let us discuss about semester 1, unit 1, vector analysis. In this vector analysis, the first topic is scalar fields and vector fields. Right. So now, before going for scalar and vector fields, let us discuss what are scalar and what is vector field. So scalar fields means that particular physical quantities. Scalar quantity means that particular physical quantity which has only magnitude. Scalar means that particular physical quantities which has only magnitude without direction. Right? Example, temperature, mass, time, etc. And vector quantities means that particular physical quantities which have magnitude as well as direction. Electric field, magnetic field, velocity, acceleration. This all comes under vector quantities which has magnitude as well as direction. Right? Now, first let us discuss what is field. Now here we have to explain about any physical quantity, either say scalar or vector. So directly explaining it becomes somewhat difficult. Instead of that, if we can express these quantities as continuous functions, right? If I take any space or region, I want to explain any physical quantity, either it may be scalar or vector. Then how I will explain in terms of if this is the particular position of a particle? Then I will explain in terms of continuous function of that particular position of the particle or position of the physical quantity. To understand this, let us take the example of rod. If you heat the rod at one end, that heat spreads throughout the rod along its length. So the temperature of the rod changes from one end to another end along the length of rod. Now, here the position of the temperature is X, Y, Z. Right? Now, here how we will express this means as a function of temperature in such a way. T is the temperature. Now we have to explain about the temperature along the length of rod. For that, we will explain it as the function of that particular positions along the length of rod, such as T, X, Y, Z. So that particular region on space explaining a physical quantity as continuous functions of positions, we call it as field. So field is nothing but this particular region or space where we explain the physical quantities as functions of that particular positions or particles. Alright. So now, first let us go for scalar field. Alright. Scalar field. Okay. So if any region or space is assigned, any region or space is assigned by scalar physical quantity. Scalar physical quantity at each and every point in the region as a continuous function, we call that field as a scalar field. We called that field as a scalar field, right? Now, such a scalar field means this particular region. Here we are explaining only about scalar physical quantities. In a simple words, we can say that in this region we are explaining about scalar physical quantities such as electric potential, etc., temperature, etc. Right? Now, such a scalar fields are having some number of surfaces. So, concentric surfaces in such a way. It has the number of surfaces. The first surface, second, third, fourth, concentric surfaces. And see here, on this particular surface, the magnitude of scalar quantity remains the same. Right? If I take example of area, I'm taking the example of area. On this surface, if area is 1 meter square, throughout the entire surface, it will be at each and every point, you will find the same value of this particular surface, scalar quantity. On next surface, the value may change. The value may change, but throughout the entire surface, the value remains the same. The magnitude of this scalar quantity remains the same on a particular surface. From surface to surface, the value may change. From surface to surface, the value may change. But on that particular surface, at each and every point, the magnitude of scalar quantity remains constant. Right? Now, such surfaces, the example are equipotential surfaces. The best example, equipotential surfaces. For example, if the potential value is 1 volt in this inner surface, potential value will be 2 volt, here 3 volt, here 4 volt. Right? But through this first inner surface, at every point we will find 1 volt only. In a second surface, at every point we find 2 volts only. In this last surface, at every point we will find the potential value same as 4 volts only. Equipotential surfaces are best examples for the scalar fields. Right? Now next, here another thing is we can choose these fields as per our convenience. How means the distance between the surface and the difference between the surface and surface. We can maintain a constant difference between surface and surface. So only we can call them as equal or level surfaces also. We call them as equal or level surfaces also. And lastly, if these surfaces are parallel to each other, if these surfaces are parallel to each other, we call them as stationary surfaces. We call them as stationary surfaces. So, this is about scalar fields. So, the first point, if a scalar physical quantity is assigned at each and every point as a continuous function, we call that region as scalar region. Now, such a scalar field consists of number of surfaces. Now, on each surface, the magnitude of a scalar quantity will be same or constant. Now, the best example for scalar fields are equipotential surfaces. The concentric surfaces are there. Now, here, another thing, the distance between or the difference between the surfaces can be taken same as per our convenience. So, we call it as equal or level surfaces. If surfaces are parallel to each other, we call them as stationary surfaces. Right? Now next, let us move for vector field. So let us move for vector field. Alright. Now definition is same. I took a region. Right? Here we are assigning vector physical quantity such as electric field, magnetic field, velocity, etc., which has the direction as well as magnitude. Vector physical quantity at every point as continuous function. Then we call it as that field as vector field. Simply, we are explaining about vector physical quantities in that particular region as continuous functions of that particular quantity. That we call it as vector field. Now here, there in scalar field we said that magnitude remains the same at each and every point on a particular surface. But here, the magnitude as well as direction, both changes from point to point. Now here, I took one surface or region where the vector physical quantity is assigned. Now here, my vector physical quantity from A, it has moved to B. From B, it has moved to C. From C, it has moved to D in such a way. Now, at each and every point, the value in magnitude as well as direction changes. Now, here, we are talking about magnitude and direction. So, we have to explain about that also. So, before explaining that, now here what I said, here, the vector quantity is moving from one point to another point in such a way. Now, let us trace the path of these vector physical quantity. Now I'm tracing. Tracing means I'm just going on joining the points. Right? I'm tracing the path of this vector field. Vector quantity. When I trace the path, I will get the straight lines or curved lines. So when we trace the path of vector quantity in the vector field, we will get curved lines. Right? So these straight or the imaginary straight or curved lines, the imaginary curved lines drawn in vector field, we call it as line of flow, or we can also call it as flux lines. The imaginary lines drawn along the path of the vector quantity in vector field, we call it as line of flow or flux lines. Correct? Now we call them as, so this is the definition of flux lines. So now we can say that vector field consists of such flux lines. Right? Vector field consists of such flux lines. It is the combination of lines of flow or flux lines. What are flux lines? Nothing but the imaginary lines drawn along the path of vector quantity. That we call it as flux lines. Right? Now first, let us talk about the direction of flux lines. Okay? Let us talk about the direction of flux lines. Now here the points I mentioned, at each and every point, I will draw a tangent in such a way. What are these? I'm drawing the tangents. Alright? At each and every point, let us draw the tangents. Now keep the arrowhead in such a way. Keep a arrowhead. Right? Now this arrowhead indicates the direction. indicates the direction. The tangents, or simply we can say the tangents drawn indicates the direction. The tangents drawn indicates the direction. Right? Now see, direction is changing or not? Yes, direction changes. Right? Now next we need magnitude. Right? Sorry. Now for magnitude, assume a small area perpendicular to the flux line flow. I assumed a small area perpendicular to the flux line flow. Now magnitude means, see, these are the particular flux lines flowing through this perpendicular area. This number of lines passing through, area taken perpendicular to the flow of lines, we take as magnitude of these lines of force or vector quantity. The magnitude of, because vector field means nothing but the combination of flux lines. Direction means the tangent drawn at each and every point on the flux line indicate the direction of vector field. And magnitude means if we consider any area or surface perpendicular to the flow of flux lines, the number of lines passing through that area indicates the magnitude of that particular vector quantity or vector field. Right? Now this is about the scalar and vector field. So vector field points, once again I am repeating. If the vector quantity is assigned at each and every point as a continuous function of the physical quantity, we define that field as vector field. The magnitude as well as direction changes at each and every point. Now if we take or trace the path of this vector quantity traveling from one point to other point, we get curved lines. That imaginary curved lines drawn in vector field, we call it as flux lines. Now, as the direction, we will draw the tangents at each and every point. So that tangents drawn at each and every point of the flux lines indicates the direction of vector quantity. And if we consider an area perpendicular to the flow of flux lines, the number of flux lines passing through that area gives the magnitude of that particular vector quantity. So hope you all understood. Stay with my channel to receive the total topics of graduation physics. Thank you for watching. Yours Reshma Physics.